Today going to introduce our speaker Balash Subramaniam Anand Narayan. Uh, he is currently a professor and chairman of Center for High Energy Physics, Indian Institute of Science, Bangalore. He did his BTech in chemical engineering from IIT Madras. Then he pursued his MSc at University of Delaware, USA, and continued his PhD in theoretical high energy physics from the same institute. He spent postdoctoral years at Physical Research Laboratory, Ahmedabad, University of Lucerne and Bern, Switzerland, and has wide collaboration in France, Germany, Romania, Switzerland, and elsewhere. His research is focused on chiral perturbation theory, collider physics, grand unification, and supersymmetry. He was awarded with Rustam Choksi Award for Excellence in Science in 2014 by Indian Institute of Science. He has written widely for general audience, have 100 plus journal articles. He has also served as associate editor of Current Science Journal and as an editor with European Physical Journal. It's my pleasure to welcome such a personality among us to give his talk on quantum field theory and role of Feynman in its development. So guys, listen carefully to Professor and ask your doubt at the end of the session. Thank you. Over to you, sir.
Thank you very much. I will not share my screen right now. I'll share it a little later. So the talk will come in some parts. First, I will introduce you to the personality of Richard Feynman. Then I will motivate the approach that he took towards the development of essentially of quantum electrodynamics in the beginning, which was later generalized to other field theories also. I'll also try to tell you the differences between the formulation between quantum electrodynamics and other field theories. That's what I was asked to do. I'll try to explain to you what are the Feynman diagrams that are named after him. And then I'll take you to a very important recent application, which is in the context of the anomalous magnetic moment of the muon. So that is how the talk will proceed. Unless there are urgent questions, we can have towards the end for questions. Okay. So let me begin. The reason why I'm not sharing the slides right now is there is a principle due to Patrick Winston, a very, very well-known professor at MIT who gives tutorials on how to give talks. So he says that we have only one language processor at any given time. So if you're listening to somebody, then you will not be able to read what they're saying. And if you're reading what is written on the screen, then you will not be listening to what they're saying. So since the main thrust of this session is that you would be listening to someone like me who is more experienced than you, so at least for the first 10 or 15 minutes, I thought maybe you could just listen to me and then I'll have the slides. Is that okay? Ms. Komal and Keshav, is that okay for you?
Yes, it is very much okay.
Okay. So thank you very much for this invitation. So it's always a pleasure to be talking to young people. After all, I too was young once and people did talk to me when I was young. So in a sense, it's only the wheel coming full circle that I'm here to talk to you about the work of Richard Phillips Feynman. So it was one cold January morning in 1986 at the University of Delaware when my classmate, now Dr. Paul Saulnier, he asked me, have you heard the news? He had a very shocked look and I said, what? He said, you know, this Challenger shuttle has just disintegrated and that there are no survivors. Many years later in 2003, when I was with some friends in Grenoble in France, we heard the news about Columbia, the second shuttle disaster. So this shuttle program of NASA is one of the great achievements of mankind. And it's sort of sad that 2 out of the 5 shuttles that they built, had this kind of a fate. And also the crew that was aboard. But it is a remarkably successful program, which did a lot of space exploration and did a lot of work in terms of understanding of the cosmos and the universe, and also carried out commercial missions and so on. Now, there are 3 surviving shuttles, Discovery, Endeavour, and Atlantis, but they're all retired. So now there is no more shuttle program. And the former USSR had designed an even larger shuttle which never took off. It was called the Buran, because the shuttle program was not completed. So the shuttle program, as you know, is one of the flagships of US science and technology. And the disaster was a huge blow to their science and technology. And then the president of the US at that time appointed the Rogers Commission to find out what was the reason for the disaster. And one of the important members of the commission, I think it had about 7 or 8 members, he looked really sad and he was shaken and he even had tears in his eyes. So someone told him and also told me afterwards that Feynman had just passed away. So Ed Kerner had been his first PhD student at Cornell University and had graduated probably around 1950 or so, could have been 1949 or so. So Feynman was not very old even at that time. He was born in 1918. So he must have been about 32 at that time, and Ed Kerner would have been about 27 or 28. So they were quite close in their age. The gap between the student and the teacher was not very much. If Kerner was someone to go by in his clarity of thought and simplicity of expression of scientific ideas, and I was fortunate to have been his student, I can only imagine what Feynman may have been like. It is my estimation that Kerner, at some level, he had been inspired, obviously, by his teacher and also imitated this style. So Feynman himself had obtained his PhD quite early from Princeton University in 1942, when he was barely 24. He had finished his undergraduate studies from MIT, and then he had been called to the war effort, indeed as many of his brilliant contemporaries were. For his PhD, he was supervised by John Archibald Wheeler, and his thesis actually is a remarkable piece of work and is even published as a small book. I will show you the references later. So Richard Feynman in full, Richard Phillips Feynman, was born on May 11th, 1918, and that is the reason why we are here today, to commemorate his birth in New York. Passed away on February 15, 1988, Los Angeles, California. And he is regarded as one of the most brilliant, influential, and iconoclastic figures in his field in the post-World War era. I have taken a lot of these notes from the biographical note in the Encyclopedia Britannica, which gives a very concise notes on his life. So Feynman remade quantum electrodynamic theory of the interaction between light and matter, and that's what I'll be talking to you about, because that's what you asked me to talk about. And he also altered the way in which science understands the nature of waves and particles. So that was the topic of yesterday's talk by Professor Shankar, where he must have talked to you about the path integral formulation of quantum mechanics. There was already a precursor to that by Dirac, but it was developed in great detail by Feynman. And so this little book that is called Feynman's Thesis also carries Dirac's 1932 article. So he was co-awarded the Nobel Prize for Physics in 1965 for this work, which tied together in an experimentally perfect package all the varied phenomena at light at work in electrodynamics. The other co-winners of the prize were Julian Schwinger of the United States and Shinichiro Tomonaga of Japan. And they had all essentially created the same theories from different ways. But it turns out that Feynman's method, or the formalism that he introduced, the diagrammatic technique that is named after him, is probably the most clear way in which the subject developed. And even today, it is Feynman diagrams that are used, although the other formulations of Tomonaga and Schwinger are all equivalent, but not as direct and not as amenable for implementation, let us say, on the computer in terms of evaluating diagrams and to figure out mathematically what those diagrams mean. So he also gave a precise rule for a diagrammatic representation of processes in the theory of interactions of light with matter, and to interpret them in terms of numerical answers, let us say, for scattering cross-sections, or for, let us say, the anomalous magnetic moment of the muon that I'm going to tell you a little bit about. So during the Second World War, Feynman was recruited to serve as a staff member of the US atomic bomb project at Princeton University for 2 years. And then he had to go to Los Alamos, New Mexico, which was for the bomb project led by Oppenheimer. So at Los Alamos, he became the youngest group leader in theoretical division of the Manhattan Project. The head of the division was Hans Bethe, and he devised a formula for predicting the energy yield of nuclear explosive. But he was later very much shaken and kind of changed by the fact that human beings had developed this nuclear explosives. And in his later years, he's talked about how, everything seems kind of absurd in such a situation where we are today armed with such deadly explosives. So anyway, so let me skip some of these things. And he was among those who observed the first detonation of the atomic bomb on July 16, 1945, near Alamogordo in New Mexico. So you see the date here is July 16th, 1945, and it was just less than 3 weeks from that day when it was dropped on Hiroshima. So you see the aim and the intention of this research was really military research. And it says that his initial reaction was euphoric, of course, who wouldn't be? I mean, such a triumph of the human mind over nature in a sense, but of course, it was destructive. So some of the key features of his life, which I have already said in some words, but it may help us put things in perspective. He was born in a place called Far Rockaway, which is a town or a neighborhood in New York City in Brooklyn. His undergraduate thesis, mind you, this is also interesting to note, as an undergraduate, he introduced an original and enduring approach to forces in molecules. And this is what goes under the name of the Feynman-Hellman theorem, which tells you how to compute some things, you see. So very, very early on, he showed his creativity. I already mentioned to you that he had done his PhD at Princeton, and he had developed the approach to quantum mechanics. So the other key milestones in his life, the associate professor at Cornell University in upstate New York from 1945 to 50, which is not such a long period, and Ed Kerner had been his student in that period. And he returned after the war. He was back in Cornell, and he worked on fundamental issues of quantum electrodynamics and other applications. These are associated with what is called the lamp shift, and also the discovery of the anomalous magnetic moment of the electron at that time, which had been detected by Polycarp Kush. So Polycarp Kush and Willis Lamb, they shared the Nobel Prize for these experimental discoveries, which had to be explained by theorists. So I guess it was the anomalous magnetic moment which had been attacked by Schwinger, and that's kind of considered to be his fundamental contribution to quantum electrodynamics. So already in 1950, he became professor of theoretical physics at the California Institute of Technology, or Caltech, and he stayed there for the rest of his career till 1987 or so, when he became too ill to continue in service. So in terms of his scientific work, and this I agree with, the biographer James Gleick, who's also written this book entitled Genius, is also the person who has contributed this piece to the Encyclopedia Britannica. So the 5 particular achievements of Feynman that he mentions are first, correcting the inaccuracies of earlier formulations of quantum electrodynamics, which I just mentioned. Of course, there's also the path integral, but it's not listed over here. So he was also involved in the processes of renormalization that I will talk about a little later. And he introduced simple diagrams, which are now called Feynman diagrams. So the whole formalism was given to him, and as we go higher and higher orders in calculations, let us say in the electric charge, the number of diagrams grows very rapidly. But the rules are still the same. It's the Feynman who gave the rules for understanding and interpreting and mathematically extracting the answer associated with any given Feynman diagram. So as we go higher and higher in the expansion of any quantity of interest to us, whether it's the muon anomalous magnetic moment or in a scattering cross-section, it'll be a series in powers of the electric charge. So as we go higher and higher, the number of diagrams also grows, but the rules are always the same. You had to use these rules to pull out these mathematical numbers associated with a particular quantity. So that is one of his leading contributions. And in the early 1950s, he worked on a problem in condensed matter physics, which has to electrons by protons, which reveals the structure of protons. Today we know that protons and neutrons are made up of quarks. So mathematically there had been a theory given by Gell-Mann, but the direct physical validation of this quark model was given by Feynman in what is called the quark model. There are also a bunch of small contributions, not as magisterial as these. For instance, just as you have the interaction of electrons with photons, which is quantum electrodynamics, you also have the interaction of so-called colored quarks with gluons. And these gluons are like the photons. They belong to a family of theories known as Yang-Mills theories. And these gluons have self-interactions. These self-interactions are a bit of a problem. And Feynman realized, based on some very simple physical arguments, that this theory is not complete, and he had to introduce today what are called ghosts, which are named after two Russian physicists, Faddeev and Popov. He found a very direct physical reason for believing that such ghosts should exist. Now, these ghosts are not seen in nature, but in order to make a calculation self-consistent, one needs to include the contributions of these ghosts in Feynman diagrams. He also has a half-page paper published in Physical Review on the mass difference between protons and neutrons. Now, all of you know that neutrons do decay. With a lifetime of about 10 minutes, a free neutron decays into a proton, an electron, and an antineutrino. So the neutron obviously is heavier than the proton, otherwise it could not decay. But what Feynman computed was that if you just had corrections to the proton and neutron mass difference due to the presence of photons, then the proton would be heavier than the neutron. So it was a paradoxical thing that he found. Today we know that there's a larger contribution to the mass difference from the quarks. The quarks that make up a neutron are more massive than the quarks that make up the proton. So there are two separate contributions to the proton-neutron mass difference. He also gave many lectures on gravitation, and he pioneered thinking about quantum computation also very early on. I think he had a collaboration with the Thinking Machines Corporation, and I think there is some work that he did over there. Then there's another paper that he wrote with probably a student, Rick Field, on something called quark jets. One of the interesting things to note about Richard Feynman is that most of his papers were singly authored. He liked to sort things out for himself. So it was only very rarely that he had papers that he co-authored with anybody. This is a model that doesn't work today because, there is so much that no single person can know everything. So that's the way it is. So there are a large number of books, and I will show you the sorts of books that are available on the life of Feynman and the kinds of books that he wrote. But I do recommend two books strongly if you're interested. One is called Genius by James Blake that I just mentioned. And then there's also a book by Sylvan Schweber called QED and the Men Who Made It. And it is a book on Tomonaga, Schwinger, Feynman, and Dyson, Freeman Dyson, who passed away only about a year ago, who was instrumental in making this theory mathematically rigorous and making it useful. Now I'll share the screen and I will just give you a brief outline of what these are, what these Feynman diagrams are. Have I shared the screen? Is it visible now?
No, sir.
It's not visible? Why not? Okay, let me see.
I think, sir, one of your colleagues is also Feynman's PhD student.
Yeah,
I think Professor Apurva Patel.
Sorry, what about Apurva Patel?
I think one of your colleagues, Professor Apurva
Yes,
Patel, was
he was a student at Caltech, and he had a lot of discussions with Feynman. Although they don't have a joint paper together, I think Apurva acknowledges his lifelong debt to the discussions that he used to have with Feynman, and I think Apurva is also thanked in one of the papers by Feynman. Is the screen visible now?
Yes, sir. Now it is visible.
So let me motivate for you a little bit about the origin of these Feynman diagrams. I'll just say a few words about what some of you have already seen in your BSc and MSc classes, and I'll try to sketch where such a thing may arise in what we call quantum field theory. So basic quantum mechanics is basically a system that you're trying to study where there's a particle that is described by a wave function denoted by psi moving around in a potential that is a function of the space, which is denoted by V of x. And then there's a kinetic energy term over here, d squared psi by dx squared, because you know how to go from classical to quantum mechanical description by replacing observables by operators and so on. And what you solve in your quantum mechanics course is what is called the time-independent Schrödinger equation, which is a second-order differential equation like this in one space dimension. So you see here there is the Planck's constant, which is h bar, h by 2 pi. H is the Planck's constant, h bar is the reduced Planck's constant, minus h bar squared by 2m d squared psi by dx squared, plus v of x acting on psi is e psi. This is a second order differential equation. And you know how to solve second order differential equations. You'll be able to do this when you have an explicit form for v of x. In most cases, you will be able to solve this only if v of x is a sufficiently simple function, like say a free particle or a particle in a box, or let us say a simple harmonic oscillator. You will be able to solve this. But let us say that for any potential v, you do know how to solve it. And then you know that there is a bunch of energy levels denoted by En, where n is a discrete label, and the boundary conditions fix what is En, and you solve the corresponding eigenvalue equation, and you get the energy levels denoted by En. And for a given fixed En, then there is a corresponding psi n, which describes that particular state where the energy is En. Okay? Now let us say that you have a potential V of x where you have already done this. And to that you add a small potential denoted by lambda of V2 of x, which is going to disturb the system a little bit. But this whole entire new potential that you have to write a corresponding Schrödinger equation for that. Let us say that you don't know how to solve it, that it's no longer such a simple problem. But still you don't get angry and unhappy and throw up your hands and say, look, life is hopeless. But you'd rather say that maybe the energy levels are not disturbed all that much, and I should be able to find the corrections to each of these energy levels En because of the presence of this additional part of this potential, which is multiplied by a small parameter lambda. And then you notice that such a thing is actually possible for you to do. That the states at the lowest level, the states do not change at all. In fact, it's still the same Hilbert space, still the same set of states that you can use in order to evaluate the correction to the energy by taking this new potential that you have and evaluate its expectation value in the old states. So that gives you a correction at order lambda to the energy. Nice, you're very happy. But supposing lambda is not all that small and you want to get the correction to order lambda squared. That is also possible because of the beauty of quantum mechanics. But life gets a little more complicated. So now you get two insertions of the potential of this perturbing potential. So now you have a correction to the energy at order lambda squared. Not only that, you have to find the expectation value now between psi n and psi m, and then sum over all values of m. So you have two such contributions in the numerator, and this is divided by the difference between the energy levels of En and Em, and you have to sum over all intermediate states. Isn't that wonderful? Quantum mechanics has this property that you can find a systematic expansion and corrections to these energy levels in the presence of a perturbing potential, order by order in this term lambda. Okay, this thing is called a perturbation series. This is something that you have seen in quantum mechanics. And this happens in a hydrogen atom and a simple harmonic oscillator. You can take the hydrogen atom states and then you can have a weak magnetic field, and you can figure out what are the corrections to the energy levels, and then you can have a simple analysis about the properties of the scattering amplitude, that it has to be a complex, has a real part and an imaginary part. And you know that the total cross-section is related to 4 pi times the imaginary part of the forward scattering cross-section. So these are all things that you know. And it's very nice that in quantum mechanics you have such a nice controlled procedure by which you can compute these things. And these lead to things that you do in your MSc courses, like transition rates of how an excited state of hydrogen atom will decay to the ground state, or a given excited state can decay into a lower excited state. Or you can also compute how it can absorb photons and a given state can go to a higher excited state and all these things. Emission and absorption of photons. So that is so much for quantum mechanics. And now we want to introduce what we call quantum field theory, because in particle physics, the energies are already so large that the kinetic energy is comparable or may even exceed the mass of the particle. So if you have such large energies, then you may not even have particle conservation anymore. You can have an electron and a positron which collide, and then they produce, let us say, a mu plus and a mu minus in the final state. The mu plus and mu minus are heavy cousins of the electron. We already said that a neutron can break up into a proton, an electron, and a neutrino. So which means we are saying here that particle type itself is not conserved, that because of the special theory of relativity, a heavy particle may disintegrate and produce a bunch of smaller daughter particles. So this means that already in quantum field theory, we are no longer able to, unlike in quantum mechanics, talk about a system with a potential and a particle and so on. Particle type itself is changing. So quantum field theory is the framework within which we account for phenomena where you're no longer able to talk about a system and various states in the system. Particles itself can change. You may have a theory where you start out with a free neutron, which then disappears and becomes a proton. So quantum field theory is when you bring quantum mechanics and the special theory of relativity together. You have to account for relativistic kinematics, where the particles are themselves moving at very large velocities close to the speed of light, let us say. So that is how you account for relativistic kinematics. And you can have particles created and destroyed. As I said, diagrammatically, I can represent E plus E minus going to mu plus mu minus by such a process, where E plus and E minus produce a fireball producing a virtual photon, which then disintegrates into mu plus and mu minus. So this is a diagrammatic way, a common sense way in which we represent this collision process. But believe it or not, this is already a Feynman diagram. It tells you very precisely how, at a particular energy, if you tune E plus and E minus in, let us say, the center of mass frame, it will tell you exactly what is a cross-section for the production of mu plus mu minus. This Feynman diagram allows you to do that. So what are the analogs of what I talked about earlier of having a system that is unperturbed and then you have a perturbation? So here the unperturbed system are free electrons, free positrons, free muons, free mu plus, free mu minus, and also free photons. And what we call, so those are the eigenstates of the system, are all these plane waves representing these particles moving around freely. But if one of them comes close to the other, if one of them comes into the field of the other, one may scatter off the other through the exchange of a virtual photon. This is not surprising because we know that charged particles interact with each other through the electromagnetic field. So Feynman rules are those precise rules which allow you to calculate a very specific scattering cross-section or a very specific lifetime, not necessarily in a theory of with photons, but a theory with, let us say, W bosons, which are the force carriers of the weak interactions. So that will tell you exactly how a neutron can produce a proton through the presence of virtual W bosons in the vacuum. We've already heard this 2 days ago from Sri Prachati. That's the reason why I'm taking the liberty to mention all these things. So, our Hilbert space of states here, the unperturbed system, are free particles represented by plane waves, and you have interactions represented by these vertices, where you have an electron and a positron which come together and produce a virtual photon like so. So that is what I have written for you over here. But there's one more complication. Unlike in the previous case where we didn't mention anything about angular momentum and spin, in the case of the Schrödinger equation, we didn't say anything about spin. Here we need to augment the discussion with the presence of spin, because we know that electrons are spin half particles. Therefore, you will not have a second order differential equation that describes relativistic, which describes the motion of an electron, but rather a first order differential equation, which is called the Dirac equation, which accounts for the spin of the electron and the spin of the positron. Analogously, we also have to discuss the spin of the photon, which is described correspondingly by Maxwell's equations for the free electromagnetic field. Okay, so I have schematically represented this thing by something called the Dirac equation, where the particle is no longer described by a single wave function, but by an assembly of wave functions which have very specific properties under Lorentz transformations, and these are called Dirac spinors, and it's a first order differential equation like this, where these gamma mu are matrices. I told you that this is an assembly of 4 objects strung along as a column vector. So in order to multiply this, you need 4 by 4 matrices, and these are called the Dirac matrices. And here there's an identity matrix which I have not mentioned. Just as for the Schrödinger equation, you have an object which is called the Hamiltonian, which describes the energy of the system. There's a corresponding cousin of the Hamiltonian in relativistic field theories. There's a cousin which is called the Lagrangian. It's not quite the Hamiltonian, but it's related to the Hamiltonian. But in a sense, it also captures the energy of these interacting particles, namely the electrons and the photons. And it's written in this way. So it is a very nice function that looks like this, that involves both the electron as well as the positron, written in this way. Then there is a part. All of you know in your BSc that the energy, that the Lagrangian of the electromagnetic field is given by E squared minus B squared, while the energy is given by E squared plus B squared. This is the Lagrangian. The energy is E squared plus B squared. I'm sure you know that. But this is a funny way of writing this, which is the relativistic way of writing the same thing, is this thing called F mu nu, F mu nu. These run over 0, 1, 2, and 3. The 0 is a time component, 1, 2, 3 are the 3 spatial components. Nothing very mysterious. Even if you haven't seen it so far, you will. And you will figure out for yourself that all this makes sense. So there is a free part over here where the electron and the positron are sitting the first term. And finally, there has to be an interaction. Has to be an interaction between the electrons, the positrons, and the photon, which is given by just this simple structure, psi bar a mu psi. So diagrammatically, what Feynman said, he translated this Lagrangian into a bunch of very simple diagrammatic rules, that there will be a straight line like this with an arrow, which represents the electron, then a wavy line, which represents the photon. Free particles, these are all supposed to be free particles which span the Hilbert space. And finally, there's an interaction term over here, which is the cousin that we have over here. The cousin in the non-relativistic case was this lambda V2. Remember that V of x is sitting inside the Hamiltonian in order to describe the Hilbert space. So the interaction, the additional interaction is this lambda V2 over here. So the cousin of the lambda V2 in relativistic field theory is this vertex over here, where you have an electron, a positron, and the photon. which you can go back and read from the Lagrangian, psi bar, psi, gamma mu. That's all. It's just order lambda squared. So analogously, in quantum field theory, you can have second order. So here there's only one factor of the electric charge. Here there are two factors of the electric charge. Here we had a sum over all possible intermediate states, sum over all possible intermediate states. Note the sigma m over here divided by this energy denominator. So here the sum over all intermediate states means that this particle which came in with, let us say, momentum p, splits into two. One of them carries a momentum p minus k and the other carries k. And k is an arbitrary momentum. So you have to sum over all possible values of k which are not bounded. So in the case of a discrete sum, you have a sigma over m, whereas in case of a continuous variable like this k, you have an integral over k. So that is why when you go to second order in the electric charge, you get an integral over all possible momenta. And just like you had here, this energy denominator sitting over here, energy denominator, there will be other denominators over here in the electromagnetic case, k squared minus m squared. This is very schematic, okay? Don't take this literally, but this is the origin of why there is a sum over all intermediate momenta and why you have these energy denominators also appearing. So Feynman showed that at this order, there are only three types of basic diagrams that you need to evaluate. One is called a self-energy, where the electron that comes emits a photon that is reabsorbed, or a photon comes, produces an E plus E minus pair, and then again becomes a photon, and then you have what is called a vertex correction. And Feynman gives very precise rules for assigning mathematical values to each of these diagrams. Now, this particular sum, this integral over here, causes a lot of difficulties. This whole thing may become mathematically meaningless. So, the presence of that sum means that some mathematical procedure has to be adopted to make these things meaningful. And that process is called regularization, followed by what we call renormalization. There are other simple processes of this kind at this order, like Compton scattering, where you have an electron scattering of a photon, and the energies of the incoming photon and the electron are changed to different energies for the photon and the electron. Bhabha scattering is the scattering of electron and positron, positron. There's something called Müller's scattering, which is electron-electron scattering. There's even light-by-light scattering, which is called Delbruck scattering. Now, these are all processes. This is a loop, okay? So this is like over here where you have, this kind of a sum over intermediate states like this. So this Delbruck scattering involves such a thing, but it happens to be finite. So it doesn't have any problems. And then there are other properties in field theory that one has to deal with, which is called renormalization, and the fact that this electric charge itself changes as a function of the momentum that is flowing into a particular loop. And then it was shown by Landau at the time that QED has some difficulties, but now we know how to handle all those difficulties. This QED is naturally generalizable to what you heard from Shirup the other day, where the electrons lines are also replaced by quark lines or neutrinos, and the protons and the photons are replaced by W bosons, or these could be colored quarks, and these are replaced by gluons, except there are also gluon-gluon vertices, which are absent in QED. In QED, the only basic vertex is the electron-photon vertex. Okay, so with this, now I want to motivate for you some recent applications. Close all tabs. Oh no, what did it close? Okay, doesn't matter. Let me now go here. This one. Is my screen still shared? Is there any problem or everything is okay? Hello? Hello? Is everything okay?
Yes, sir. Everything is okay.
Okay, fine. Now let me tell you a bit about the applications of this to a very recent experiment. Am I intelligible? Are you people able to follow what I'm saying? If there's anything, you can just stop me there, and then I can see if I'm
Sir,
understandable or not.
can you just explain, sir, why these like mathematical steps are converted into the figures? Can you just explain?
Okay, sure. Just one sec. This one. Okay, that's a good question. So here, let us go to the Lagrangian, basic thing. Okay, so here you have psi bar d mu psi. Okay, so this over here translates to the first line over here. Okay, it means that there is one psi over here and another psi over here. That's how you get the line that joins psi bar and psi. Similarly, deep inside this, I have not written that out. It's called d mu a nu minus d nu a nu, which is actually the kinetic energy for the photon. Okay, it's the kinetic energy for the photon. So if you actually expand that out, you will find that there is a term that contains an a mu and an a nu, two photon fields, and that is what represents this propagator for the photon. And finally, when you go to the Lagrangian, you see that there's only one single term, psi bar a mu psi, which also has this electric charge over here. So that's the unique term for the interaction. There you have psi bar, which represents the positron, psi, which represents the electron, and a mu. Okay, so that's how you get this vertex. Now, given these vertices, now you want to draw diagrams which uses only these three as ingredients and nothing else. Okay, so if you want to have a loop like this, what can you do? You can take this particular thing and take this over here and then join it back over here, you get the first one. Okay, then you have this E plus E minus. So this, you kind of square this diagram over here, then you get the vacuum polarization. And then we also have the possibility that, can you see my cursor? That a photon is emitted from one line and is absorbed from the other line. That gives you the vertex direction. So this first three basic ingredients, if you want to produce the next higher order diagram, that is quadratic electric charge, by just drawing these basic objects, this is the only way in which you can join various lines and vertices in order to close them in a self-consistent manner. Okay? Did that make sense?
Okay, sir. Okay, I understood.
Okay, great. Okay, now let me talk about an application of this to a very recent, interesting, and important experiment. And in any case, for you all to kind of, attach a name and a face. So here we have Feynman in the top left, and this is Tomonaga on the top, and Schwinger over here, and then this is Freeman Dyson. So Dyson is also included here because he kind of made this whole procedure of extracting these infinities in those diagrams and making the whole theory sensible. He tried to put that on a rigorous footing. So there's something called a Dyson series that is associated with quantum electrodynamics. So let me talk to you now about this important project, and some of you may have seen some of these slides in my earlier talks. So this has to do with the precession of a muon in a magnetic field. So a muon is a heavy cousin of the electron, and classical Dirac theory predicts that it has a magnetic moment of a gyromagnetic ratio of 2. But it turns out that this 2 is a classical number which holds for classical Dirac particles. But in the presence of interaction due to photons, that number changes and gives rise to what is called the anomalous magnetic moment of the muon, which is measured by the way in which it recesses in a constant magnetic field like this, gives the velocity. So this is how, if you immerse a magnetic, so what is meant by a spin-half particle? It means that this behaves like a tiny magnet over here, whose magnetization points along this red vector over here, and if you immerse it in a B field like this, it will precess and go round and round and round. Of course, this is an unstable particle and it eventually decays, but as long as it is alive, it is going to do that. And if you turned off the weak interactions, it would be infinitely long-lived and it will just keep precessing round and round. The question is, blob, this yellow. What I showed you in my previous slides was the lowest order in QED correction to the QED vertex. But if you go higher and higher, you'll have more and more and more and more corrections, all of which here. So the order of magnitude that we are expecting for this value G minus 2 is this. So recall that quantum electrodynamics has only one parameter in addition to the mass of the electron, and that's the electric charge of the electron. So if you take this E and then multiply and square it, E squared and divide it by 4 pi, it leads to a very important constant, which is the combination that it appears in atomic physics and is named after Arnold Sommerfeld. It's called Sommerfeld fine structure constant. It's called the fine structure constant because it determines the scale of the fine structure of the hydrogenic lines. Okay, that's why it's called the fine structure constant. In contrast to, let us say, the hyperfine splitting, which also exists in atomic physics, which has to do with the interaction of the electron with the proton spin. The fine splitting is related to the orbital motion of the electron and its interaction with the spin. Okay, so that's the hierarchy. So there is the fine structure, and then there is the hyperfine structure. So this also fixes the scale for the Thomson cross-section, which is related to the same combination. The Thomson cross-section is a cross-section of the scattering of low-energy photons of electrons. Okay, so E squared 4 pi, if you just put all the constants and so on, is a number of the order of 1 by 137. There is also a significance to this number 1 by 137. It is the velocity of the electron in a Bohr orbit, in the lowest Bohr orbit, in units of the speed of light. Okay, so you can see that there is another physical significance to the Sommerfeld fine structure constant. So if you take this 1 by 137 and further divide it by 2 pi, then you get a number which is roughly 1 by 860, which is 0.00116. So this is very small. Okay, doesn't matter, but this is very accurately measured today. So there have been many experiments over the years which have been measuring the anomalous magnetic moment, first of the electron and later of the muon. And there's a current ongoing experiment about which you may be reading from time to time, which is the Fermilab muon G minus 2 experiment, which is a repeat of an earlier experiment which ended in 1999 or so, and finally wound up in about 2003 or 4. So as I said, the muon itself is an elementary particle which is about 210 times as heavy as the electron, and it decays just like the neutron decays into a proton and electron into a neutrino. The muon decays into an electron and two of the neutrinos, and actually its lifetime is very well known. It's of the order of 2 microseconds. Its mass is given in these units over here where I put C to 1. And I want to draw your attention also to this very interesting, most recent measurements of the Sommerfeld fine structure constants, where alpha is 1 by 137 point this. And there is a different measurement. One comes from rubidium atoms, another comes from cesium atoms. And you see that they don't quite agree with each other. This is another puzzle, but I don't know exactly what this actually signifies. Anyway, so you can see that this particular number that I mentioned over here, 0.00116, is now measured to much, much higher accuracy over here. I've taken out this factor 10 to the power of minus 11. 116592040. Look at the precision to which it is measured in the Fermilab experiment. And the theoretical value is also known to very high precision, and these two don't agree with each other. That's the real problem. You see here, look at these numbers, 2040 with an uncertainty of 54, whereas here it's 1810 with an uncertainty of 43. So you see these two numbers do not agree with each other within the errors, and that is the reason why this is such an interesting and important experiment. So in order to get this theoretical number, it is not just drawing the lowest order QED diagram and then saying, I've evaluated it and I've got alpha by 2 pi. This has to be evaluated to much higher precision and much higher order in the electric charge, and also loops involving other particles in the full standard model. It's not just quantum electrodynamics. So as I said, this is a roundup of what is the standard model, what is quantum electrodynamics, and how quantum electrodynamics was formulated by all these original authors, and where we stand today. So let me show you here what this is. This is the magnetic moment of the electron, which was measured already in 1948. So you're looking at almost 74 years ago. This was measured by Polycarp, Cush, and Foley. So he was awarded a Nobel Prize for this. And you see the number that he sees in his very first experiment is here, 00119, with an uncertainty of 00005. You see the very first measurement itself was very much on the ball. What we are showing was 116. The first experiment 75 years ago, he had already seen it at 0.119. Control, no, Apple, 0. Okay. So this is the theory paper from that time by Schwinger, where he actually evaluates this. What happened? Oh. Go back. Okay. So you see over here, he gives a number 0.001162. This paper published in 1947, and the entire paper is just 2 columns in letters to the editor of Physical Review. Now, this is such a stunning result that it actually appears on his gravestone. So that is Schwinger, who had given this very concrete prediction at that time. And later, this whole theory was cleaned up by Feynman, for which he got the Nobel Prize. So you see, at one loop, it was finite and computed by Julian Schwinger to be this particular number. And this has to do with how we understand quantum field theory and the production of particle pairs from the vacuum, which correct a particular observable of interest to us. Here is a set of representative calculations that we have to do today in order to evaluate the anomalous magnetic moment, contributions from various particles. This is, for instance, various hadrons like protons, pions, all sorts of particles which make a correction. I have myself worked in this particular sector, which is called C. There is also this hadronic light by light scattering, which is the analog of Delbruck scattering that I had mentioned. Here is a diagram that comes from the electroweak sector of the theory, for instance. But let me show you another one. So this is from a paper, Ayoma et al. This is the Japanese, who calculated the order of 20,000 diagrams at this particular order. This is a small subclass of diagrams, entirely in QED, by the way. Only electrons and photons. No W, no Z, no gluons, no nothing. Of course, they may have muons and other electrically charged particles, but no other interactions. Look at the complexity of the diagrams that they have to evaluate. These are what are called rainbow diagrams over here, large class of such diagrams. And to actually evaluate these diagrams, it's not just about drawing diagrams. After this, you have to figure out, do all those loop integrals associated with each of these things and extract that particular number from this, which consumes a lot of CPU time on supercomputers. So you see, physics is also challenging computing at the frontier. The experimental apparatus for this determination is like this. So these are these particles called pions. I'm sure you've come across them. They are the force carriers inside nuclei. But if you smash protons into each other, they'll produce a large number of pions. And these pions decay into muons, which are all polarized with their spin. They are like spinning tops. So they collect all these spinning tops, purify this beam of muons, and inject them into a ring over here. And they go round and round and round. If the muon had no anomalous magnetic moment, then its precession frequency would be exactly equal to the frequency that it takes to go around the ring. Why? Because that's just a fact of life. That's how it is. The so-called spin equations determine that. But the fact that in nature there is an anomalous magnetic moment means that after a while, this muon starts pointing in a different direction because of the anomalous precession. And that direction in which it is pointing after having traversed part of this ring is measured by the decay electrons that come from the muon. It's an ingenious measurement principle that is used in order to carry out this measurement. Okay? And this is done at very high statistics with millions of such muons going around and these decays being collected. So, in this talk, what I have tried to show for you are various aspects of the personality of Richard Feynman a little bit. I didn't want to talk too much about him because your organizer had told me that essentially what you wanted to know were his contributions to field theory. So he gave the complete set of rules that are needed for any such perturbation theory. As I said, it's not just about photons, it's not just about electrons. Get a corresponding set of Feynman rules for the electroweak theory, for neutrinos, for quarks, and so on. That is his contribution to field theory, which is what you wanted to know from me. So, since a picture says 1,000 words, I just wanted to show you this collection of books that I collected. Many of them belong to me. Some of them are from our library. Some I have borrowed from a friend. So this, as you know, is the famous lectures of Feynman, which he gave to first-year students, 1962 or so, which are collected and edited and written by Lighton and Sands in addition to himself. Those are the three. Feynman and Hibbs, the book at the bottom, where he does quantum mechanics and path integrals. Then there is his later lectures on gravitation that you see over here. And Venkatraman has written a book on QED, the jewel of physics, which is very nice. Then there's a book over here. I can't see what it is. Let me see if I can make this any bigger. There's Feynman's thesis. I think this is his book, Feynman's own book on QED, that is between the thesis and Venkatraman's book. He has written a book on statistical mechanics, which is a very good tech book. He has these lectures on computation. This is his collection of some of his letters. And this is one of his books on particle physics, which is called Photon-Hadron Interactions. He talks about his contributions on the parton model. So that is one of his books. Let me show you the other collection of books that I have. So this is the book that I mentioned by Schweber, which is QED and the Men Who Made It, Dyson, Feynman, Schwenger, Tomonaga, James Gleick, which is his kind of definitive biography. Here is a collection of his letters edited by his daughter. And various collections of lectures, things that he wrote, popular books. Surely you're joking, Mr. Feynman, sitting up here. And then there is also What Do You Care What Other People Think? That is also there somewhere. And here is so-called Lost Lectures, which is over here. Then his not so easy pieces. There are two collections from his Feynman lectures. One is called 6 Easy Pieces and 6 Not So Easy Pieces. This lost lecture was a bunch of unedited notes of his and some various recordings which existed, which were all cleaned up and put together by Goodstein and Goodstein. Okay, so this is what I wanted to show you, and in order for you to relax a little bit before we go into our session, I wanted to play for you this 3-minute video that we can all watch together, and then after that we can go into the discussion section, if it is agreeable for you. Is it okay for you?
Yeah, it is very much okay. Thank you very much.
Okay. So let me play this now, and let's see.
One way, it's kind of a fun analogy to try to get some idea of what we're doing and try to understand nature, is to imagine that the gods are playing some great game like chess, let's say a chess game, and you don't know the rules of the game, but you're allowed to look at the board, at least from time to time, and in a little corner perhaps. And from these observations, you try to figure out what the rules are of the game, what the rules of the pieces will be. So you might discover after a bit, for example, that when there's only one bishop around on the board, that the bishop maintains its color. But later on, you might discover the law for the bishop is it moves on a diagonal.
Okay, so I just thought that I would leave you with that, and then I'd be happy to take questions. I'll just stop the presentation.
Thank you very much, sir. Very nice talk. At the end, Feynman talk what science is in a very clear manner. Uh, Thank you very much, sir. Sir, if anyone have questions now, they can ask.
There's something in a box over here. Ah, thank you.
Hello, sir.
Yes, hi. Yeah, tell me.
Sir, you have shown many books at the end of the session. But according to you, we must read. Which book we must read, according to your opinion?
You see, it all depends on your interest. Often, learning about the lives of scientists can be very interesting and inspirational because many of them did come from difficult circumstances, as you saw Feynman himself. He had to work through the war, the Second World War, and probably when he was a kid, there was a Great Depression in 1929. So you see, when you learn and read about the lives of these people, you also get an impression about history and the forces that shape them. So it's a matter of your taste. There are some people who like to learn about people and what they do. There are others who are only interested in mathematical aspects. So this kind of thing. I think many of his books are actually a little advanced. So it is not really advisable. You try the Feynman lectures, but I'm not very sure. The Berkeley series, for instance, is probably more accessible for students. So you can probably hear one or two of his lectures which are available on YouTube. That could be nice. So I can't really give you advice on what you should read. So surely you're joking. Mr. Feynman is an interesting book, and, to get an idea. So everybody needs something to inspire them. So I've given a vague answer, but probably that's the best I can do.
Yes, sir, that's fine.
So you were explaining about muon G2 experiment and also about the magnetic moment. Sir, currently now in Fermi lab also experiment takes place. Sir, is all that experimental details, sir, are matching up to the precision that
No, they're not. So there is actually a discrepancy, which is at the level of 3.3 sigma. That's what I had mentioned, based on the data obtained in the first run of the Fermilab experiment. Now, more data is being analyzed. In the coming months, we should have an announcement about the new data and the full analysis. So, if this widens the gap between theory and experiment, we really don't know why it is. It may be some interactions beyond the standard model which is responsible for this, or maybe there's some experimental effect that we do not understand. Or sometimes these things happen in life. Theory and experiment somehow do not agree. We are talking about very fine, very precise measurements and very accurate calculations. We don't know what the source of this discrepancy is. So it's an exciting time in a sense. As Feynman himself said, you're looking for that one small thing where things do not match, and this seems to be one of them. There are one or two more such examples with the decays of B mesons, mesons that contain a B quark. There are some data which have a problem. There's a recent announcement, the measurement of the W mass from an old American experiment at Fermilab, which also disagrees with other measurements of the W mass. So there are many little corners like this in elementary particle physics, where there's a mismatch between experiment in theory or some experiments and a new experiment. So these are, in a sense, exciting times. But the main thing in particle physics is still the dark matter. We still don't know what is the source of dark matter, what is the nature of dark matter, which is present in the universe. That much we do know. And also, of course, we do not have a quantum theory of gravity. Nothing that I mentioned today anywhere has Newton's constant in it. Gravitational constant is not present. So it is a theory where we are just assuming flat space-time and everything is against such a background of flat space-time. But we do know that Newton's constant is present, but it is very far away. A quantum theory of gravity would set in at a much, much higher energy scale or a much smaller length scale than the ones that we are accustomed to. Okay.
Okay, sir. One more question from my side, sir.
Yeah.
Sir, also, sir, when we study the thesis of his the Feynman, the thesis was on the path integral formulation.
Yeah.
Sir, how that is connected with the things that he discovered later, like
Yeah, it's a
renormalizability
very
and other.
important. It's a very important question. This whole business of taking this classical Lagrangian that I wrote down for you and to be able to draw those straight lines and the vertex and so on was made much easier by the availability of a path integral formulation. Although it's equivalent to other formulations of quantum mechanics, this particular formulation of principle of least action and so on, the path integral proved to be very useful for extraction of interactions in other settings. For QED, it was not that important, but when it came to non-abelian gauge theories or Yang-Mills theories, the path integral formulation, presence of Faddeev-Popov ghosts, all those things become much more transparent in the path integral formulation of field theory. So Feynman essentially produced the correct toolkit to do the analysis for other extensions of quantum electrodynamics, such as the electroweak theory and quantum chromodynamics, which is the theory of strong interactions. That's a very good question. And we also understand many other phenomena, such as the presence of anomalies, which leads to, say, the pi zero decay into two photons using the path integral formulation. Of course, there's always a price to be paid. What is done in a transparent way in path integral, often there are other difficulties elsewhere, like in renormalization and so on. So all the experts have figured out various techniques to go back and forth between various formulations of quantum field theory. Did I answer your question?
So, sir, I got something, sir. It is of what I got something.
Okay, thank you.
Sir, one question last. Sir, as we are celebrating the Feynman's birthday, the great physicist who contributed a lot work on various problems of physics, perhaps almost the difficult problem that were taken in his lifetime. Sir, what advice you want to give to us so that we can also work problems and can contribute?
I think now it is very important that you also work in areas where there are good job prospects, not just go into very theoretical areas. Use of computers is very important. You should have no fear of computers. And I think applications oriented, at least for the next 10, 15, 20 years, you should look. And Feynman is a person who had a lot of respect for experiments and experimentalists. If you want to continue a research career, I would strongly urge all of you to stay in experimental physics. Theoretical physics, the opportunities are few and there's a lot of competition. So my advice to you would be to be, theoretically strong, but try to work in experimental or computational fields.
Okay, sir. Thank you very much from my side.
Thank you.
Thank you very much, sir. The session is really very great.
Thank you.
We learned a lot from you.
Thank you. Thank you for having me. So I think we can leave the meeting now.
Okay, sir. Thank you very